Okay, now we're going to talk about converting from 3D Cartesian to spherical. Previously, in the last two videos, we talked about converting from rectangular to polar and equivalently rectangular to cylindrical. And we found that their respective formulas were given by the integral f of xy dx dy, any order, is equal to the double integral of f of r cosine theta, r sine theta, is times r dr d theta. And this was from 2D Cartesian to polar. For 3D Cartesian to cylindrical, it was given by this formula. dx, dy, dz. In this situation, we have the triple integral, f of r cosine theta, r sine of theta, and I might run out of space, so I'm going to move a little bit to the side. So we have z, r dr d theta dz. Notice that the difference between these two is simply by a height. So therefore, we can see that converting from polar to cylindrical is just adding a height z to it. Now, what happens if we were to convert from 3D Cartesian to spherical? First, I'm going to draw the picture again. We have our x, our y, and our z. And we are intending to convert this into some kind of spherical shape with one, a flat radius r, and a general radius rho. Here in this situation, we need the relation between x, y, and z to r, and in this case, theta, phi, and in this case, theta. So the relation is given by x is equal to rho cosine of theta sine of phi. Y is equal to rho sine of theta sine of phi. And z is equal to rho cosine of phi. The reason for this is if we were to take just a sliver of x versus y, and we looked at this right here, or apologies, this is z and y. This represents rho, while this angle represents theta. This whole section represents, it represents phi, and this represents theta. This whole section represents r. So the relation between phi, r, and rho is given by rho being equal to r being equal to rho sine of phi, and r is equal to z is equal to rho cosine of phi. And if we took a glimpse of it a little further, the angle is right here based on symmetry. So as such, when we first plugged in cylindrical, we have x equals to r cosine theta. But plugging this in, we have rho cosine of theta sine of phi. Y was equal to r sine of theta, but is now equal to r sine of theta cosine of phi. Z was also equal to z, but in this case we show that this is rho cosine of phi. Now, I challenged the viewer, and I will show the general formula later on about how we can find the Jacobian. I challenged the viewer to verify that the Jacobian, or the scaling parameter that you do get, is equal to r squared sine of phi. Therefore, that the conversion from Cartesian f of x, y, z, dx, dy, dz is equal to the conversion in triple integration of f rho cosine theta sine phi, rho sine theta sine phi, and rho, apologies, this should be rho squared, rho cosine of phi, rho squared sine of phi d rho d theta d phi. Here, as with cylindrical coordinates, we use spherical coordinates because some objects are better off with spherical symmetry compared to Cartesian symmetry. For example, when we are discussing about the concept of Gauss's law, if we were to put a charge inside here, finding the electric flux across each surface requires divergence theorem. The divergence theorem we will discuss later on. However, this becomes much easier if we were to have something that's more uniform throughout, and we were to put the charge in the center, then every point that the charge penetrates for its electric flux is equidistant. And as such, we'd be able to find the electrostatic field easier. Similarly, we would be able to find the magnetostatic field easier too, although this was always equal to 0. So that is one reason why we would want to use spherical coordinates. And I challenged the viewer to show another use of spherical coordinates. All right, thank you.